In this video, we're going to talk about drawing Lewis structures, but we're going to focus on binary compounds where the central atom is one of our period 3 atoms. The nonmetals in period 3 are silicon, phosphorus, sulfur, and chlorine. And while we're doing this, we can note that this also applies to period 4 and 5 nonmetals as well. If we're considering our period 3 atoms, what makes them different is that in period 3 atoms, the valence electrons have a principal quantum number of 3, right? Remember, if n equals 3, then L can equal 0, 1, or 2. 0 signifies s orbitals, 1 signifies p orbitals, and 2 signifies d orbitals. Now, the m sub L values tell you how many of those there are. Well, there's only one m sub L value, so there's only one s orbital. There's 3 m sub L values for L equals 1, so that's 3 p orbitals. And there's -2, -1, 0, 1, and plus 2. So there's 5 d orbitals with 2 electrons each. That gives space for 18 electrons. Now, we very rarely see an atom, a central atom, with 18 electrons around it. But this does tell us, right? When we were in period 2, we were limited to 8 electrons because we only had s space and p space to use. When we're in period 3, we can actually go above 8 electrons because we can also use d space to accommodate more than 8 electrons. So the biggest difference when we're drawing Lewis structures with period 3 atoms in this middle, in the center of the structure, is that we sometimes, not all the time, sometimes can have more than 8 electrons around that central atom. So let's look at a molecule like this, SF4, or sulfur tetrafluoride. Right? Fluorine is our most electronegative element, so sulfur will have to go in the center with fluorine around the outside. Right? If we add up our valence electrons, right, then we have sulfur contributing 6, and we have 4 fluorines, which would be 4 times the 7 that each fluorine contributes. That's 6, that's 28. It gives us 34 total valence electrons to distribute. Right? We have 4 bonds, right? Each of which is 2 electrons. So that means we can subtract 8 of those. 34 minus 8 is 26, leaving us 26 electrons to distribute, starting from the outside in, creating octets. So fluorine already has 2 around it, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, right? So we've accounted for 24, leaving 2 left, right? Well, we can't put them around the fluorines. The fluorines are in period 2. they only have room for 8 electrons in their valence shell. But sulfur is in period 3. And so even though sulfur would prefer to have an octet most of the time, in this case, when forced, it's got enough room to accept another pair of electrons. So there is an unshared pair of electrons on that sulfur, and that leaves 2, 4, 6, 8, 10 electrons around that sulfur. Now, if we're concerned, one of the things we can look at is a property called formal charge. Right? So the formal charge is related to the number of valence electrons that an atom brought minus the number of electrons that same atom has control of in the final Lewis structure. And that is, right, so it's going to be equal to the valence electrons minus, right, and an atom controls all of its unshared electrons and half its bonding electrons. Okay? So the formal charge here is going to be, right? We said sulfur brings 6. Right now, right, as we drew it, it has 2 unshared electrons, and it has 2, 4, 6, 8 bonding electrons equals, right, 6 minus 2 plus 4 equals 6 minus 6 equals 0, right? And so having a formal charge of 0 is a preferred state for atoms in structures. And so in this case, right, because sulfur has the extra space, it can have 10 electrons around it instead of just 8, right? And so that is the big difference when we have atoms from period 3 as our central atom. Sometimes, not all the time, but sometimes they can have more than 8 electrons. They can have more than an octet in the final Lewis structure if we can minimize their formal charge by doing that. Now let's look at a molecule like PF3. Phosphorus trifluoride. Okay, so phosphorus is the less electronegative atom, so the phosphorus will have to be in the middle, and the fluorines will have to be around the outside. Right? We have to add up our valence electrons. Right? Phosphorus gives us 5. 3 fluorines give us 3 times 7. That's 5. That's 21. Gives us 26. Right? Our 3 bonds already account for 6 of those, leaving us 20 to distribute. So we start around the outside, putting them down in pairs. That accounts for 18, leaving us 2. The 2 have to go then to the central atom to give it an octet. But if you look here, right, here's a situation where we're out of electrons, right? We're out of valence electrons to distribute. Our central phosphorus has 8. Our fluorines around it have 8, right? Everything has an octet, and we're happy, right? So atoms in period 3, if they're in the center, don't have to have more than 8 electrons. As a matter of fact, they would usually prefer to have only 8 electrons. But in some structures, we find that that central atom can have more than 8. Now let's consider the molecule ClF3, chlorine trifluoride. So we draw a connected structure. Right? Then we add up our valence electrons. Right? So chlorine has 7, and 3 fluorines is 3 times 7. So that's 7 and 21. That's 28. Right? Our structure already accounts for 6 of those, leaving 22. So if we start around the fluorines, since they already have 2, we can put 6 around each one. Right? So that takes away 18, leaving us with 4. Those go as pairs on the central chlorine, right? So each fluorine, 2, 4, 6, 8. Around each fluorine, the chlorine has 2, 4, 6, 8, 10. It exceeds the octet, but it can do that because it is in period 3 and has room for more than 8 electrons. And if we want to check, right, if we want to do our formal charge, right, our formal charge, the number of valence electrons chlorine brought, which was 7, minus the number of unshared electrons, which is 4, plus half the electrons in its bonds, which is 6. So we have 7 minus 4 plus 3 equals 7 minus 7 equals 0. And so that central chlorine has no formal charge. And so that makes us more confident in our structure.